noticed.
Yeah, I noticed it when I came in, but we were talking about it.
It is actually far more efficient compared to Windows. It takes less time to start up, and I run certain types of applications like Eclipse. It uses Java. It's a pretty heavy-duty program. It's really kind of takes up a lot of memory and it's complex. When I use Windows as an operating system to start it up, it takes forever, and it's loading from the internal hard drive in that case. But when I use Linux, which is using an external USB hard drive, and we are talking about USB 2.0 here, not 3.0, and everything just runs like zippy. We're done. So I just have a lot of questions about the efficiency of Windows.
I thought you said it couldn't run Linux. Are you doing it in virtual machine?
No. This is actual Linux. What I did was I redid the distribution, the ISO image, and this is really funny. When it did not work, I was using the proprietary driver from NVIDIA. And now I'm using the open source, non-proprietary version of the driver, and it works okay. Which is really strange, yes.
Yeah, for its purpose.
Quick question.
Yep.
I already know the answer to it.
Go ahead.
I just want to make sure. With the A bracket I subtract 1,
okay.
The value of I being, in the beginning of our homework, for example, let's say it's 3. Do we take A bracket I subtract 1 and just subtract the value of I? Say, for example, it's 3.
You mean like this?
Yeah. So what we do? So
is that on the right hand side or left hand side?
It's on the right hand side.
On the right hand side. Okay, so the left hand side is what?
And it'll take A bracket I.
Okay.
It would replace. Yeah.
Okay. So the way you do this is you have to evaluate the stuff inside the square bracket first. So you have to look at this entire expression and say, okay, it comes out to a particular value. Okay, I'm just using an example here. So let's say I is 15 at this point. Okay, so let's say I equals to 15. So this expression evaluates to a constant of 14, an actual integer value of 14. So once it evaluates to 14, then you can apply the square bracket operation and say, okay, let's look at element 14 in array A, and that becomes the value on your right hand side. And then on the other side, because I is 15, so I is just 15, which means A bracket I is referring to A bracket 15. So you look up the array and look at element 15 in the array and say, I want to take this value, which is the value of A bracket 14, and copy it to the column representing A bracket 15.
Okay. So my confusion was, even if it was only temporary, A bracket I being the value of that specific, let's say, array cell 15, do you use that value in array 15 for a subtraction? So if A value of A...
No, the subtraction applies to I.
Yeah.
So I minus 1 is just taking the value of I and subtract 1 from it. So when you're just performing this part here, it has absolutely nothing it has nothing to do with A at all.
Okay. This in the method I just explained, would the negative 1 be outside of the bracket?
What if minus 1 is outside of the bracket?
Would that be?
Then you will be looking at the value of an element in the array and then subtract 1 from that.
Perfect.
Yeah. So the square bracket in many ways is kind of like parentheses, round parentheses. You basically have to perform that calculation before you perform the actual square bracket operation, which is the indexing operation. All right. Any other questions regarding the homework that's due on Thursday? No questions? All right. So if there are no questions, I'm going to get started with searching in the sorted array. This is what we are talking about today, but I'm not going to read my own notes, because I just don't need to. So what I'll do instead is I'm going to explain the rationale of the algorithm itself, go through a few examples by hand, and then we'll go ahead and actually try to write the algorithm in a step-by-step fashion. The first thing we do is to kind of recap our story on last Thursday. Okay, the competition, the programming competition between me and Pat. Okay, so the question now, to you is in your future classes in CISP 360, 400, For those of you who want to become software developers, you will probably encounter cases where you really just want to implement an algorithm to get something done, and not necessarily start from scratch. I mean, why do you want to come up with a sorting algorithm from scratch when there are decades of researchers and smart people already thought of really good ways to doing it, right? Okay, so you can just go to Wikipedia and pick up a sorting algorithm. The question is, how do you find one, or how do you select one that is efficient? Okay, so that's the question. How do you find one and select one that is efficient? So what you can do is you can look up sorting algorithms using Google, and it comes up with Wikipedia, has an entry to that whole thing, and I don't need to really zoom in that much because it's really a whole lot of little details. But what you need to do is to find out which one is efficient, and you can see that it even has categories of items here. Simple sorts. So with simple sort, we have insertion sort, selection sort, and even bubble sort. Those are simple to implement sorting algorithms. When you look at the algorithm, it's fairly short and easy to understand. Efficient sorts, which includes merge sort, heap sort, and quick sort, they are longer if you look at the algorithm themselves, but they are more efficient. So how can I tell something is simple but not so efficient, as opposed to something that looks kind of complex but it is actually more efficient, especially when you look at execution time? So that's the first question that I want to answer today. So we'll take a look at bubble sort first. Okay, so we'll open the tab here and compare that to merge sort. So there we go. We have bubble sort here, and I have just been here a little bit earlier. And bubble sort has its own page, but what I want to do is to show the main article here. Go to bubble sort, and what we want to do is to take a look at the algorithm itself first. It has examples and stuff like that, but this is basically the algorithm implemented in a programming language called Pascal. And you can see that most of the things that we talk about in this class, is actually here too. This is actually not Pascal, it's actually a pseudocode too. And you look at the other sorting algorithm, which is merge sort, and this is the main article of merge sort. And then we skip all the way to the algorithm itself, which is down here, top-down implementation. And you can see that, hey, that doesn't look simple. I mean, that looks quite a bit longer than the other one. Do most of you agree that when you look at merge sort, it looks more complex? I mean, you look at the notation here, it's longer than bubble sort, which is just that much. If you just compare the number of lines of each sorting algorithm, I would say merge sort is about 2.5 times, close to 3 times as long in terms of the number of lines, as opposed to bubble sort. Bubble sort is one of the simpler ones. Okay, so most people, not knowing anything about algorithm, will instinctively say, I'm going to implement bubble sort because it's a shorter algorithm. It has to be, a more efficient one. That is really not the case. So the question is, how can you look at an algorithm and know that it's not efficient? And the answer is, you cannot. Okay, you cannot judge a book by its cover. So in algorithms, you cannot judge an algorithm by the number of lines. What you need to do is to go to what we call a big O notation. So I'm just going to cheat here and use the search feature and look for big O and then open parentheses. Okay. And we will take a look at okay, so even among big O of n-square sorting algorithms like insertion sort are usually considerably more efficient. And we wanted to get, okay, we'll just focus on this sentence here, okay? It just says, it's big O of n squared complexity means its efficiency decreases dramatically on lists more than a small number of elements. And I know that animation is kind of distracting. It's basically showing you bubble sort in a graphical way, because that's how elements basically start to line up and become sorted in the end. Okay, so now we want to look at the big O notation and go like, what is the big deal of the big O notation? which has nothing to do with Japanese anime. It's actually not completely Japanese. It's actually, I think it's a cooperation between the Japanese animation house and, was it, never mind, nobody knows about it. It's about Look it up, Big O anime. You know, there's a big robot. But it's interesting. It's has a very interesting backdrop, to that story. So anyway, Big O of n squared. What it means is n in this case is representing the size of the problem. In other words, how many elements are we dealing with in an array? That's bar a bar to us. Okay. So Big O of n squared means the execution time is proportional to the square of the size of the array. Which also means if you double the size of the array, it will take 4 times as long to finish the algorithm. If you triple the size of the array, it will take 9 times as long to finish the algorithm. If you quadruple the size of the array, it will take 16 times as long to finish the algorithm. All right? Okay, that's one. Let's look at merge sort. Okay, merge sort. The time complexity is usually listed at the beginning. So in this case, the merge sort has a worst case performance, which means it cannot be worse than this, of n times log n. Okay, so which one is better? If you just plot out n squared as a curve, and you plot out n times log n as a curve, which one do you think grows faster?
N squared.
N squared. Okay, and n log n, even though it is still worse than just n or log n, it is better than n log n. I mean n squared. Excuse me. It's better than n squared. Okay, because of this, it means if you have to choose between bubble sort and merge sort, you should choose merge sort for efficiency. Now, why is that important? Okay, I would bet you a lot of programmers do not take this into consideration. They just pick one. They just pick whichever one seems to be the easiest to implement. And then what happens in that case is if you choose the one that is easiest to implement and you test it, right? I mean, most programmers will actually test the program with simple test cases like a few. Okay, but when you have an array of we will just take the example up there with the animation. If you take an example of only 8 items, the advantage of n log n may not be that important. Okay, it may not be measurable, and you will just say that, oh, why do I want to waste all that time to implement something that is a lot more complex? And in the end, it doesn't seem to do anything that is actually useful. But what if the problem size doubles? What if it quadruples? What if it it gets bigger and bigger and bigger? What if it becomes 100 times larger than your test case? Then the complexity starts to become important, because now n log n is going to grow a lot slower compared to n squared. Okay, and that's one thing that you have to consider when you choose a particular algorithm to do something. Because when you just look at sorting algorithm, okay, if you just look at the sorting algorithm page here, it's listing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are at least 11 well-known sorting algorithms. So how do you choose one? Why do you want to pick one instead of another one? Well, time complexity is definitely one consideration. Now there are other things about these algorithms that will kind of make one better than the other one. Like within efficient sort algorithms, quick sort, versus merge sort. One is suitable for one type of application, and the other one is much better for other types of applications. Merge sort, interestingly, is a sorting algorithm used by old mainframe computers that do not have hard drives. How do you store information before they have hard drives, running on computers?
Floppy disk.
No, the floppy disk came, pretty late too. So how about before floppy disks?
Punch cards or the
Tapes. Okay, to do mass store, they use tapes. Okay, so let's say you have a tape of student records that are not sorted. Okay, so they're all over the place. How do you sort, items on a tape? That's pretty hard. I mean, if you think about it, it's pretty hard because a tape, like a video tape, like VHS, some of you may not even have seen VHS because you guys are much younger, right, than me. So you may not have
Not
seen
that
a
young.
VHS at all. So you look at a VHS tape and go like, what is that?
I think older generation,
Wait.
yeah, the younger generation would not know what VHS is.
Exactly.
Like, because most people here are at least 18, and pretty sure they know what VHS is.
They have heard of their parents mentioning
They've heard the
VHS.
stories of old.
Yeah, they dug up all the old stuff and go like, what is that in the garage, Dad? You know.
It's like that's a VHS.
Before your time.
Yeah, exactly. How do I play that thing? It won't fit into my computer.
It won't fit into my DVD
A lot
player.
of people playing Call of Duty don't understand what people meant by the Xbox One looking like a VCR.
Yep.
What's that?
Yep. So, but with
I think everybody in here knows what VHS is, but do they know what an 8-track is?
8-track, yeah,
Yeah.
8-track was a great idea, but it did not fly. Yep.
I don't think I know what that is.
Okay, so imagine that you have VHS tape, to store your data, and you have to sort items on that tape. Okay, that's really not easy because you have to go back and forth a lot. If you think about sorting, with something, you kind of laid it out, and you kind of change the order of things. You move this one all the way from here to over here and do stuff like that. You cannot do that efficiently when you're dealing with reels of tape. And guess what? Merge sort can do that really, really well, and they do it with very little memory too. So that's why merge sort is actually a very interesting sorting algorithm, because it came from the 50s when mainframe computers still run on tapes, and is extremely efficient with that sort of thing. All right. So now that we know what is a big O notation, it's basically just a notation to tell you how the execution time scales up with the problem size. We can kind of now say, okay, binary search is superior, okay? Because if you look at searching algorithms, well, actually, we don't have to even look at searching algorithms. We'll take a look at merge sort. Now, with merge sort, okay, I did not mean to click it. With merge sort, the worst case performance is big O of n log n, which means when the problem size scale up, when n, which is our bar a bar, scales up, the execution time is increasing using that curve, which is n times log n. Okay, so in your mind, you probably are thinking, well, are there any better sorting algorithms out there? I mean, is this really the best, or can someone think of even better sorting algorithms with a better time complexity, more efficient sorting algorithms? And the interesting thing is, computer scientists can actually prove that this is the best you can do. No one, no matter how smart, okay, using technologies that we currently have, using computers that we have, cannot come up with an algorithm that can beat this time complexity, period. Okay, so when you move on to a 4-year university, for those of you pursuing computer science as a major, you will get into a class called the analysis of algorithms, or otherwise known as algorithm analysis, same thing, and they can prove mathematically that they cannot come up with an algorithm more efficient than merge sort. Okay, well that's kind of interesting and useful too, because once you get to n log n, you know that you are done. Okay, this is as fast or as efficient as it can go. Sorry?
Doesn't get any better.
It cannot get any better. Okay, and with sorting, with searching algorithms, if you look at binary search, it is the same way. When you look at binary search as a searching algorithm, it has a worst case performance of log n, and you cannot come up with an algorithm faster than binary search. Okay, if you start with an array that is sorted, and you can only do certain types of comparison, this is the best you can do. Okay? Which is kind of helpful, because it means don't waste your time trying to come up with a search algorithm that is faster than this, because you cannot. Mathematically proven. All right. Are there any questions about these claims? Yep.
That's like saying there's never going to be a better government than capitalism. It's just a matter of time.
Well, in this case, it is not. Okay, because there's a difference between this and political science, between this and even physics. Okay. okay, what is the main difference between computer science and physics when it comes to is this possible, or how do we explain something like this? The main difference is physics is not a man-made science. Physics is there to explain natural phenomena. Okay, and when we have better equipment, we can start to figure out things. Hey, that's not exactly what we think it should be. It's off by a little bit. Okay, so when we don't have really good high accuracy timepieces, we cannot possibly understand what is time dilation because it cannot be measured. Okay, you cannot say that, hey, when we travel really, really fast, the clock on the rocket ship is slightly off compared to a ground-based, clock. Okay, just by a little bit. Okay, it's only with better equipment that you can start to say, hey, they're off by a little bit, or you can observe a star, and when the star is kind of close to a heavy object like the sun, you can actually see the light bending. It's like, well, that star is not supposed to be there. It's off a little bit. Why is it off a little bit? Well, it's because of the gravitational pull of the sun bending the path of the photon, so that it appears to be at a different place. Okay, but before we have telescopes, people look at stars and go like, the sun is too bright to begin with. I can't really see anything. Done, right? But what about computer science? How does a computer work? Is it something that comes natural and we just say, here's a magical box that does certain things and we want to explain how it does things? Or is it really just the opposite? We make this machine to operate in a certain way. It's the second case, right? So that's why in computer science, we can say that we can mathematically prove certain things and say that it is impossible, because we invented the rules to begin with. But in natural science and political science and all other type of sciences that are here to explain things that is just naturally happen, it's not the same thing, because you can never say that it is not possible because we just don't understand the full nature of how things work.
Might it start changing with the quantum computing?
Yes, it will. Okay, but this is based on deterministic machines that we currently have. Yep. So once you change the underlying computing mechanism, yes, these will change as well. Yep. Go ahead.
I mean, we didn't create mathematics, though. We just discovered it, and there's still discoveries that we haven't found.
Well, mathematics is actually a man-made thing too. It's what is one? What is the concept of one?
Mathematically, those things they've always been there. We've just discovered it, and
it's math the way we describe it.
It's logic that's always existed.
Math
so
is
whether we put it into action.
it is more like a language than anything else. Math is more like a language where you can use it to describe things, to express certain things.
Right.
Because in nature, there really is no such thing as this. It does not exist. It's a concept. It's a language thing. We use this to describe this one, right? Singular. That's one single thing. But in nature, there's really no such. There's no one thing called one in nature. And in nature, there's no multiplication either. This is how we describe things. And we have to set up the rules of what is the product of two numbers, right? A times b. We have to set up all those things.
those things are going to be like that, whether we describe it like that or not. That's always going to be how we live as human beings.
Right, but we arbitrarily define it as that.
That's how we define it, right? But that doesn't mean it didn't exist in the first place.
Well, we can define, all kinds of operators. There's an infinite number of operators that we can define. It's just, are they useful? Right? Some operators you can define it to do whatever you want it to define it, as. But, as a system, those operators may not be useful at all. These just turn out to be useful on a daily basis. It's a language that we use to describe other things. Like when you have, when you're taking physics classes, we use multiplication, division, integration, and stuff like that to model, to try to describe, how things work. But that's really just a description. How things actually work is something entirely different.
It's like if you're in sports and you're planning, you're making a game plan, you can't just plan to punch the other guy in the face. That's impossible. It's basically kind of how I see it.
In a way, but math is yeah, but math is a language. Mathematics is a language, and language is definitely invented, right? I mean, if there's no person alive, then there's language has no use because no one's going to use it. Same thing with math.
So you're saying no matter, the only thing that's going to make this process faster is technology, not
It's changing fundamentally how computers work or how computing works. This number is based on having a single processor that potentially has an infinite amount of memory, and there's a certain way you can access memory. So it's based on all those rules. Then we come up with these numbers and say you cannot do any better than this. But you can change the rules. Okay, if you use quantum computers, you're changing the rules because now you can do things that we currently cannot do with machines like these. Yep. But these are all based on basically man-made rules, artificial ones. Yep, it certainly is, and that's why computer science is not a science. Because it's not natural. It's not a natural science. It's actually a field of mathematics. All right. So now we can get this out of the way. And then the second thing we want to do once we understand, okay, what is time complexity, why it is important, and not really how to derive these things. That's not really in the scope of this class. We can take a look at a example of using binary search, and we'll do it by hand first. And then after we do it by hand a few times, then we'll try to come up with an algorithm to do it. Because that's the whole purpose of this class is algorithm design. But we cannot design anything, we cannot tell a computer how to do something until we know how to do that one something, right? All right, so let's start with a sorted array. Okay, so we'll just punch in some random numbers here. And I can actually do something like this. Let me see if there's a random. I think there are multiple random things. I'm a little obsessed with just a little bit with doing this in an automatic way. And where's random? Okay, there's RA and between. Okay, that's nice. Okay, this is random between, so I can basically specify a random number between the two numbers. So we'll go ahead and click it, and we'll specify. That's okay. That's fine. That was intentional. So we'll have 0 and 5, but we'll also make it add to the number before. So this one, the next number is always larger or equal to. So we can just drag it down, and now we have our. Maybe I'll change it. I'll change it so that it has to start with 1. Because otherwise it just has too many numbers that are the same. There we go. Okay, so I kind of like this. All right, so now we have a list of numbers that are sorted. Okay, just by the way these numbers are created, we make sure that these numbers are sorted. And we want to go through this and go. We want to search for certain things. Okay, we want to search for a particular value and see how binary search works. Let's go ahead and shrink it. You guys can tell me what number you want to search for. Just pick a number out of this list, or something that is even out of this list.
19.
19? Okay, so let's look for 19 here. Now with binary search, how does binary search works? How does it work?
You said you divide it in half in the middle. And
Okay.
search top or bottom, or search one of them.
We compare to the one in the middle, and then we can rule out some possibilities. Right. Okay. So out of these 7 items, which one do you think is the middle one? The one with a value of 12. Okay. So this one, the one on row 4, is has a value of 12, and that's the one in the middle. So we want to compare 19, which is the value that we are searching for, with 12. And the conclusion is easy. I mean, everybody can come up with this conclusion right away and say, okay, 19 is greater than 12. That's good, okay? This is one comparison. Knowing that 19 is greater than 12 is good. But you know what? Because the array is sorted already, from just one single comparison, I can also come to the conclusion that 19, which is what we are searching for, is also greater than everything before this. Just because the array is sorted I can make that conclusion. Is that making any sense? Yeah. So that means I can now look at this one here and say that, you know what, 8 is also less than 19, or whatever is here is less than 19. I don't know that it's 8, I just know that it is less than 19. Whatever is here, I don't even know it's 5, it is less than 19, and whatever is here is also less than 19 because the array is sorted. So anything before the element containing a value of 12, they all have to be less than 19. If they're all less than 19, they cannot be 19. So that means I have now just ruled out of 7 items, I have ruled out the first 4. I have 3 items left that may contain the value of 19, and I'll pick the one in the middle. And the one in the middle is this one, and that turned out to be just 19. And so, our process is done because I have just found what I'm searching for. Yay. Yay. All right, so let's go ahead and copy this and paste it here. And I want to paste just the value. Let's see if I can do that. And I don't want to paste the formula, just the values. So they end up with exactly the same values. This time let me select which one to search for, because I want to search for something that's tricky, like 13, okay? Because 13 is kind of tricky because it's right there, almost in the middle, but it does not exist. So how can we make the conclusion that 13 does not exist? Okay, so let's look for 13 here, and the first comparison is still compared to the one in the middle, and we can say that 12 is less than 13. Okay, that's good. Basically the same kind of conclusion that we had last time, because if 13 is greater than 12, it's also going to be greater than everything before this element. So I don't even need to look at this value and say, oh, 8 is less than 13. I know it is less than 13 because the array is sorted. So we can now come up with a whole bunch of conclusions after the first comparison. And then in the second comparison, I only really have 3 choices left that can still be of the value that I'm searching for, which is 13. But I picked the one in the middle to compare to, which is this one here. 19 is greater than 13, and because the array is sorted, I don't even need to look at the value of the last item because I know it is greater than 13 anyway because the array is already sorted. Are there any questions at this point why I can come up with those deduction and rule out more items than I have just compared to? No questions? Okay. So at this point, I have ruled out 6 items out of 7, and we have only 1 item left, which is the one on row 5 with a value of 15. So we perform this comparison and say that 15 is greater than 13. But because of that, we also come up with the conclusion that all of these items are also greater than 13. Now, if you look at one row, each row at this point, is there any row left that can contain the value of 13, meaning that row is not less than nor greater than 13? There's nothing left. Okay, so at this point I have to come to the conclusion that 13 as a value does not exist in the array. Is that okay? All right. Now, the nice thing about using a formula in this case is I can paste it here and then I can make it arbitrarily larger. In other words, I can make it, let's pick 31, which is a power of 2 minus 1. Okay, it's 2 to the power of 5 minus 1, which makes it very nice and even because I can pick out the quote-unquote middle one pretty easily this time as well. Okay, so, but I do have to change the font size a little bit to, well, I guess I cannot really display all 30 at the same time unless I hide some of the toolbars. Do I want to do that? I can shrink it maybe just a few times more. Well, that's good enough. That is good enough. Do you guys want me to search for a particular thing? Hopefully something that does not exist because that's more fun. Looking for something that does exist, is not nearly as much fun.
56.
So for 56, all right, 56 does not exist, and it's between 2 things. Let's look for 56. Okay, 56 does not exist. What would be the first element that I should compare to? How do you calculate the row number that we're comparing to at this point? The first row is row 1, which is not consistent with indexing because the first index is 0. But since we're dealing with rows here, we do have row 1. And then the last row is row 31. So how do we calculate the row number of what we're supposed to compare to?
And then add 1.
And then add
12
1.
plus 1 divided by 2.
Oh wait, subtract
Add 1
divided
to
by 2,
31
add.
and divide by 2. Gives you 16.
Is the first row number plus the last row number divided by 2. Right? If you have 3 rows, it becomes row 1 plus row 3, which is 4 divided by 2 is row 2. Okay, so this is how you can quickly check whether some a concept works or not, is to use smaller cases, okay, smaller test cases, and you can just kind of manage it. Go like, okay, does it work? Yep, it does. So that means row 16 is the one in the middle. Okay, so we want to compare this to 56. So we'll say that 56 is larger than 52. But as a result of that, we also know that everything before 52, they all have to be less than 56. I don't need to do each individual comparison, one single comparison, and now I can rule out every single other one, before this one. And I just found that, so this one is also less than 56. So we'll copy and paste this.
Just so you don't do all of that.
Yep, copy.
And you just do 56 and
drag it?
Yeah.
Nope, it's too smart. Let me show you what I mean by it is too smart. Okay, I select this whole bunch and do the drag over here. See what happens?
Well, it's not a false statement, but it's not what we're looking for.
Correct. So I kind of have to do it the long way like that.
Well, we already got it, so I don't think we do.
That's okay, but I do want to kind of show you, how many items we are ruling out after one single comparison. If I have 8 billion items here, one single comparison will rule out 4 billion. 1/2 of what is left, basically. Okay? That's really the power of binary search. With the remaining half, which is down here, I will have to pick the beginning or the middle point between row 17 and row 31. 17 plus 31 is 48. 48 divided by 2 is 24. So this becomes the new middle one. Okay? We do a comparison here and we say, 75 is greater than the value that we are searching for. And as a result of this, we can also now rule out the other ones. Everything below this we can rule out because they cannot be equal to 56. They all have to be greater than 56 because the array is sorted. So now we have how many left? We have 7 elements left. With the 7 elements left, which is from row 17 to row 23, once again we do the average. 17 plus 23 is 40. 40 divided by 2 is 20. So this becomes my new quote-unquote middle element. And we compare this to 56. 64 is greater than 56. Okay, that's fine. So after the third comparison, now we know everything after this will also be greater than 64. Will also be greater than 64, and we can rule all of those out. And I'm going to be a little bit lazy here and just do it by copy and paste. All right. So after 3 comparisons, we went from 31 items down to 3 items. Okay? So we now only have rows 17, 18, and 19 left. And the method works also in this case. It's just that in this case we don't have to use that method, but it's a good way to double check to make sure that the method does work. 17 plus 17 plus 19 is 36. 36 divided by 2 is 18. So it does work, in general. Okay, so we look at this item here and say 55 is less than 56. Okay, cool. Very spacey.
Sorry, I forgot that.
Yeah.
All right, so what we'll do is we'll be lazy and just copy and paste a bunch of stuff. All right, there we go. Well, we got one item left, okay? Because if you look at one row here, okay, let's let's take a look at row 13. Row 13, we already know it's less than 56. In fact, we double confirm it is less than 56. If you look at these rows over here, if you look at row 22, we confirm it's greater than 56. But if you look at row 19, there's no confirmation whatsoever. Okay, one, we have not performed a comparison on this row yet, and two, using the comparison of all of the other rows, we could not come up with any conclusion whether this is either greater than or less than 56, which means it can be 56 at this point. We just don't know yet. Okay, so that's why we have to perform one last comparison and say that, oh, 59 is greater than 56, so it is not what we're looking for either. And then we can just copy and paste the rest. And at this point, if you look at each and every single row, it would have an indication whether it is greater than or less than 56, which means that we have now ruled out every single row to be of value 56. 56 does not exist in this array. Are we doing okay so far with the logic, just doing it by hand? In other words, if I give you an array of 63 items, how many comparisons do you think you will need to come to a conclusion? 6. Yep. Because 63 is 2 to the power of 6 minus 1, and that's why you only need 6 comparisons to come to any conclusion. Within 6 comparisons, because if you're lucky, the first one is the one that you're looking for, and you're done. But in the worst case, you only need 6 comparisons to come to a conclusion. All right. So I think we have enough, test cases, or we have done this, algorithm by hand enough times that we can try to come up with an algorithm to do it. Yep.
What was the equation you just used? For the
2 to the power of n minus 1. Yep. So if when you look at 31 plus 1 is 32, and 32 is 2 to the power of 5. That's why the numbers all work out nicely, and you don't end up with like something in between two
What
rows.
happens if you do?
You just pick one or the other. Yeah. Binary search is fairly forgiving about that sort of thing. All right, so let's go ahead and try to write the actual algorithm to do it. Just because we know how to do it by hand doesn't mean that we can actually do it with an algorithm. So what we'll do is we'll try to write this algorithm by hand, and of course we have this done already from before. So we'll do a Control A, select all, and delete.
That's unfortunate.
No, it's good. Each time I do this,
It's not very efficient to do it over and over again.
But that's my job. My job is to do the same thing over and over again. Oh, by the way, talking about doing something over and over again, your exam 1 is graded.
Yeah. All of it?
All of it. All 4 questions are graded, and they're grouped into exam 1 as a category. So if you look at exam 1 as a category, that gives you the score of exam 1 itself. We have quite a few people getting perfect scores. I don't remember whether your gradebook shows your ranking in class. If it does not, and you want to know that, let me know, and I can turn on the ranking part. It does? Okay. So the ranking part is basically, you see a number like, whatever, like 10, and then the slash, and then the actual number of people in class. So that is not a ratio of your score, because that would kind of suck when you get 1/44. It is actually telling you that you're ranked 1 out of 44. Okay, so the smaller the number before the slash, the better. Okay, but in this class you don't have to be super competitive, because the grading, in other words, the grade assignment part is not curved. Okay, so it doesn't really matter that you are 43 out of 44. If your score, is in the range of an A, you still get a grade of an A. Okay, it's not like, okay, only 3.5% of the entire class, can get a letter grade of A. I don't grade my classes like that. But there are professors who do that, especially at a 4-year university. Do you guys know that sort of thing or not?
Berkeley.
Berkeley?
He does that a lot.
Berkeley does it a lot, and even Davis, sometimes would do that. They would curve it. And according to many people, they have taken classes where, like the best score of the entire class is like 60 something sometimes out of 100. And so if you use the absolute scale, then the entire class is going to get D's and F's, right? So they have to curve it and basically say, okay, so assuming that the number of people who deserve A's remain constant regardless of the makeup of the class is constant. So they would just say, okay, the first 5 people in the class would get A's, the next 15 would get B's, and so on.
It seems like really inaccurate way of grading it.
Because it's based on a potentially invalid assumption of the quality, the distribution of quality of students remains constant from one class to the next. So that may or may not be a valid assumption. It also depends on another assumption, which may not be correct either, which is the difficulty level of the exam. Because because they make everything float in that case. It's not like I have one absolute standard as what I consider as excellence in the class, and we just kind of make it float. So in that case, if you have an entire class of underperformers, you will still end up with A students, which does not make sense. Or if you end up with an entire class of overperformers, everybody's getting like 90+% in the test, you will still end up with C's and B's because there's a quota to fill with B and C students. So it doesn't make a whole lot of sense to me.
Yeah.
Yep. And this is being recorded, and some UC Berkeley professor probably can hear this and have a video response to me. It's like I disagree with this. But the grading by curve has sometimes unexpected consequences. I'll answer your question first. Go ahead.
I was wondering where exactly the test was labeled on your grading.
Are you looking for it right now?
Why? See my
It's
grading.
on the bottom.
It's a category. You have to look at the category total. So you have to look at X1, Q1, X1, Q2, X1, Q3, X1, Q4, and then at the bottom of that, should be a overall score, grouping all 4 together.
Failed, bro.
Well, the highest score, I rescale everything of the exam to 20, for the 20% of your final grade. So that's why when you look at X1 itself, it should scale from 0 to 20.
Okay, so X1 has all 4 questions in it?
Correct.
Okay.
It is an aggregate of the 4. And then each one, if you click on each one, it will give you the rubric grading of each question. And if you look at question number 4, the rubric is like this long. I have to scroll like multiple times to finish grading that one. It took me an hour and something just to grade one question, that one. So anyway, where was I? Oh, that's right.
Curving.
Yeah, curving, assigning letter grade by curving sometimes has an unexpected, side effect of, students not wanting to help each other. Because, with a class with a historical record of, having to use curving to assign letter grades, and let's say, well, it doesn't really affect underperformance all that much, because, if I help you, we're all going to be in C range anyway, so it doesn't really hurt anything. But with people in the A range, because there's only a certain percentage of people who can get A's in the class, if you help out a friend who starts off at about the same level as you may end up bumping your own grade down to a B as a result, because you help out your friend now is just edging you out by a little bit to get a better grade. So it really kind of nurtures a super competitive, to the counterproductive level type of atmosphere in classes. And you're starting off with students with 4-point-something GPA to begin with. Don't forget that at Berkeley. So, is it really a healthy type of learning environment? I don't know. I would not subject myself to that.
My friend went to Berkeley right out of high school.
Mm-hmm.
Straight A student, high GPA. And he goes to Berkeley and people are stealing backpacks and destroying flash drives.
Exactly. They steal backpacks not for the value of the content in the backpack.
Yeah,
They
destroy
do it.
his homework.
Yep. You destroy the homework. They break into lockers to sabotage projects, and so on. It's crime. It's crime, but not based on economics. It's not based on, okay, you got a really good calculator, I'm going to steal your calculator and sell it for money. I steal your calculator so that you cannot use it. So you would end up with a lower grade. And then magically your calculator will appear somewhere, after the exam.
It's not stealing. I'm just borrowing it for a certain amount of time to give it back to you. It's not stealing if I give it back to you a little later.
Well, you're still taking something without permission.
Some people like to consider it borrowing for extended time.
Yeah,
Fill the time
extended.
with 6 cents.
It's borrowing, they've got to ask you for permission.
Oh yeah. I hate when that happens.
So
Always
anyway,
forget.
so that's something that you might need to consider because most of you will transfer at some point. So you have to find a school to transfer to.
With good luck.
CSUS do they do that a lot?
I don't know. I don't think they're as competitive though. Yeah, because you don't start off with basically straight A students who have to be competitive through middle school and high school to get those super perfect scores. So they are not just 4.0. They have scores like 4.3, 4.5, and then on top of that, they also have like student leadership, student government experience, good at sports, and all of the other things. Because just having a 4.0 GPA means nothing when it comes to application to Berkeley when you're coming out of high school. As a transfer student, it's different. It's a completely different student because many of those straight A students coming out of high school get burned out within the first 2 years of a UC system school. So within the first 2 years, the computer science program will have a lot of drop-offs, and as a result, their third year classes and the fourth year classes cannot have enough students unless they take on students from community colleges transferring out of a community college. And from personal experience, most of the students as transfer students going to UC Davis at least, because that's where I actually taught a class as a final year design project class. Most of the transfer students are at least as good as the students who started off with UC Davis to begin with. And many are actually slightly better. They're more realistic. They know how to work with other people. They just have more skills.
Something you really don't develop when you're trying to break into other people's lockers. Or at
Well,
least
that's
not
a
those
different
good
kind of skill.
people
Yes,
skills.
that is a different kind of skill.
Appropriate skills.
Yes, that may. Well, some people take those skills to work too. After they graduate, they go to work, and they apply the same skills to move up the ladder.
Yeah.
Yep. All right, well, let's go back to the skill that we are supposed to talk about in this class, which is how do you write an algorithm? How do you design an algorithm? Okay, this I think is really the hardest part of teaching this class is how do I teach you guys the thinking process of designing an algorithm? Okay, that really is the most difficult part to teach. All the other stuff, the technical stuff, fairly easy. It's really black and white, it's just like mathematics. But this part is hard because it is not really black and white. Okay, so once again, we'll start with revision 1. And with revision 1, we just want to capture some really, really vague concepts related to this algorithm. So we want to kind of look back at what we did with this algorithm here, and also just in terms of concept of any search algorithm. Do you think the process is repetitive? Am I doing something similar, but just multiple times?
Yes.
Yeah.
Okay, I would say it's somewhat repetitive. So we'll go ahead and just say that it is repetitive. And we do that by saying it is just some kind of a loop. I don't even know whether it's a pre-checking loop or a post-checking loop at this point, and I don't care. Okay, I just want to write down something that I can capture at this point. The loop does exit, okay, in most cases. And when does it exit? Well, when you look through these examples, okay, when do we exit? Well, it looks like there are 2 reasons to exit from this algorithm. The first reason to exit from the algorithm is, well, guess what? We just found what we are looking for, okay? So when an element matches the value, okay, so I'll just call it the key, okay? Usually the key is the term to refer to the value that we are searching for in a search algorithm. So I'm just going to use, quote unquote, the key to refer to the value that we are searching for. Okay, so that's one good reason to exit. What about the other reason to exit?
Key does not exist.
The key does not
Inside the
exist.
array.
Okay, that's a good way to describe it. So we'll just say the key does not exist in the array. Okay, cool. Done. First revision.
When it comes to the sound.
Okay, now we have revision 2. Now revision 1, even though it looks really vague, does not resemble code at all, it still has importance, okay? Because it really helps to guide you think in a way and go like, okay, now that we know we have to somehow express an element matches the key, and also we have to express somehow the key does not exist in the array, maybe we should clarify those terms. And so instead of using quote unquote the array, the key, an element, maybe we should change those terms to use variable names and also operators that we already know, we have introduced in this class. So what we'll do in revision 2 is simply to clean up the terms a little bit so that it becomes more clear. So we'll just say that, okay, let's name the array. Okay, let A be the array and let K be the key. All right, so now that we have these two terms defined, let's see if we can clean up the description of the algorithm here. Okay, when we say an element in the array, implicitly it's quote unquote in the array, matches the key, that means we are matching something about A with something about key, K, which is the key, and it's an equality. But when you look at this expression, it doesn't really make a whole lot of sense because an array has many elements, right? So there are many values. So which one is matching K?
A about.
It doesn't say, right? So what we want to do is to say, well, it's not the entire array that we are talking about. We're talking about a particular element in A that has the value of K. But I really don't know how to express what is inside the square bracket at this point. I don't know how to calculate or find that value. So you know what? I'll just be lazy and say TBD, to be determined. Okay? I'm just saying that I know it involves A. I know it involves a square bracket because I want to specify a particular element in the entire array. And I know I have to match it to K through an equality. That's all I know at this point. Fine, okay, no problem. We'll have TBD to express things that we cannot, we don't know how to express at this point. Okay. Now with this one, it's a little bit harder. The key does not exist in the array because we can easily specify it does match a particular item, but there's no easy way to say that none of the items has this value. Okay. Yep. Go ahead.
Oh, I was pulling off of a real array. I think you said for that type of a statement, the current one does not match. You wrote a sub I bracket does not equal K.
Okay, but that is only saying that one element does not match. It doesn't say that the entire array does not match.
Would that just
Right.
be A then, since A represents the whole array?
Well,
A does not equal K.
as it turns out, there's a different way to represent it, so I'm going to defer that. Okay. Because if I want to express, all values do not match, all values in the array do not match K, that kind of implies that I have to compare to each and every single one, which means, this is going back to linear search, okay? Because you're using linear search to confirm that none is matching. So it's not going to be any better than the usual linear search algorithm. Okay? So now we go to revision 3, and in revision 3, we kind of want to talk about, but how do we know the key does not exist in the array? So we go back to the example. So this is why you have to do it by hand a few times first, because now you can go back to the examples that we did by hand, and then we say, okay, in the examples that we did by hand, within each process, in each step, how did we decide that the key is there or not? Or is there anything else that we can search or we should search in the array? So we'll go back to the spreadsheet here, and then we look at this particular example. And each column in each case represents the result of one comparison. After this comparison represented by column B, can I just say that, okay, we're done? Can we say that one element is matching K? Well, obviously not, right? Because in the first column, or in column B, we are comparing to row 16, which has a value of 52. And the only conclusion about that comparison is 56 is greater than 52. It's not conclusive. Okay, the first condition does not match because we could not find a particular element that matches K, so it doesn't match. But the second condition also does not match because what about all of these items from row 17 all the way down? After one comparison, I cannot conclude that those things do not match the value that I'm searching for. Is that making any sense? So it doesn't match either condition. Okay. What about after the second comparison? Okay, after the second comparison, which is a combination of column B and column C. After the first two comparisons, we have ruled out everything from row 1 to row 16, and then also from row 24 to row 31, we have ruled out those items also. Did we make a match to K? No, we did not. Can we conclude that the key does not exist in the array? We cannot, because we still have row 17 all the way up to row 23 that we cannot conclude anything about. Is that making sense so far? Okay. So where do we make a conclusion? By the time we get to the fifth comparison, after the fifth comparison, then we can make a conclusion and say, oh, you know what? At this point, every single row is ruled out, because they do not match 56. So at this point, we can say that the key does not exist in the array. Okay? So if you think about it this way, it is the existence of elements that we cannot rule out that keeps the algorithm going. Okay, I'll repeat that sentence. It is the existence of elements that may still contain the value that we are searching for that keeps the algorithm going. The first condition I'm not too concerned about. Okay, A, open bracket TBD equals K. I'm not too concerned because it's just one comparison matching the value that we are searching for. That's easy. Okay, I'm not too concerned about that. It's the second one that I'm concerned about. How do we know the key does not match anything? So instead of saying that the key does not match anything, we can also turn it around and say nothing in the array matches K. Okay. So we'll go ahead and make that switch and basically say just change the language just slightly here, and then we can say no element in the array can match the value of K, which seems to be talking about the same thing, but it's slightly different, okay, because of the phrasing is a little bit different. Okay, we'll call it revision 3. In revision 4, then because we are now looking into our traces here, and then we noticed that we are actually tracking what in the array may still contain the value of K. Okay, so it started off all the way from the beginning, all the way to the end. Before the first comparison, anything in the array may have the value of 56 because we have not performed a single comparison. After the second comparison, after the first comparison, then we only have this much of the array left that may contain the value of 56. After the second comparison, we have this much left. After the third comparison, we got this much left. After the fourth comparison, we got 1 left. After the fifth comparison, there's no match left. Okay? So maybe we need a way to keep track of which portion of the array may still contain the value that we are searching for. Are we doing okay so far? Okay. So we'll go ahead and in revision 4, I'll just write down a hint here and say need a way to track which portion of the array may contain K. Okay. Now, if I have a way to do that, okay, I don't know how to do that just yet, but if I have a way to do that, then I can replace this condition here to basically say the portion of the array that may contain K is empty. Is everybody following the logic here? I'm translating from no element in the array can match K to the portion of the array that may contain K is empty. Now, the reason why I made that change is to match this observation that we need a way to keep track of which portion of the array may still contain the value that we are searching for. Are we doing okay so far? You're going from revision 3 to revision 4. I'm just tweaking the language a little bit, but each tweak gets us closer to the actual algorithm. All right. So at this point, I need to focus my attention to finding a way to keep track of which portion of the array may contain K. Now, when you look at the spreadsheet, it's like, by this time we have looked at it so many times that it doesn't really give you a whole lot of insight anymore. So what we'll do instead is to switch this to an analogy of a phone book, okay? So this time we're looking for a particular name, using the last name first and then the first name in a phone book, which is the normal way of how a phone book is sorted, which is good, okay? But with this time we want to apply binary search. So how would you apply binary search on this method using a typical physical phone book? And I can give you, an infinite number of little post-its or bookmarks and stuff like that to help you remember, things. So how would you do it? So let's think about it. You have a pretty thick phone book. Okay, so this is looking at the phone book from the side here. How do you keep track of which part of the phone book may still contain the name that you're searching for? Sticky notes, okay? How many sticky notes do you need to keep track of that? A lot. Or is it?
Not that many, actually.
Not that many, because the range of the phone book that may still contain the name that you're searching for is always contiguous. Okay, it's always somewhere, but it's always contiguous, which means you cannot have like chunks of the phone book that may contain the name that you're searching for. It's always just one chunk. The question is, where does that chunk begin and when does it end? So how many post-its or bookmarks do you need to remember where's the beginning and where's the end of a chunk of a phone book? You just need 2. Okay, very good. So initially, before you make the first comparison, you have to say, okay, this is the first page of the phone book that may contain the name that I'm looking for, and this is the last page that contains the name that I'm looking for, that may contain the name that I'm looking for. Because this is before the first comparison, you cannot rule out anything at this point. Is that making any sense? Okay. So between these two, you want to find, quote unquote, the middle page. Now, I know that by the time you do a calculator thing and find the exact middle page, it's going to take a lot of time. So with a phone book, you don't have to find the exact middle one. You just go to like, I think this one is about in the middle.
Close enough.
Close enough, exactly. So with binary search, if you just do the quote unquote close enough approach, you might be adding a few comparisons to the overall number of comparisons, but it's not that. Okay. In other words, this may not give you exactly. It would still be log n. It's just not log 2 of n. So you might be slightly worse than that. Okay, but you will still be preserving the general complexity of the algorithm. Okay, so you pick this one to compare to. Okay, so you hold up the name that you're searching for, and you look up the entire page and say, okay, it's not there. Okay, and of course within the same page you can use a mini binary search within that page. So you can basically say, okay, it's not on this page. All right, so let's just say that all the names on this page is they are supposed to be after the name that you're searching for. Okay, so everything on this one single page is after the name that you're searching for. You're looking for a last name that starts with M, and everything on this page starts with O, let's say. Okay, so what do you do? What do you do with these 2 bookmarks?
You bring the one on the bottom up.
Bring the bottom one up. Okay, so the question now is, do you want to bring it up to this particular page, or do you want to bring it up to one page before that? One page before, because we already know this page does not contain the name that you're searching for. And what is the purpose of the bookmark? It marks the end of the page that may still contain the name that you're looking for. But since we just confirmed that this page does not have the name that you're searching for, we have to put the bookmark one page before that one page, that same page. Is that making any sense? Okay. So this is step 1. And then let's say, then you picked out, the quote unquote close to the middle page of this entire range, the first portion. And let's say, all the names on this page, you're looking for something that starts with M, and everything here, they start with J, okay? So what do you do at this point? The entire page, starts with J, you're looking for something that starts with M. Go ahead. You move the top. Yep, you move the top one to one page below the one that you just compared to. Okay, and you keep this process, right? Until what?
You either find
until you either find the name,
or you
because
find out that
you got lucky, or
find it's not the phone.
But how do you know, using just the bookmarks or the post-its, how do you know that the name does not exist in the entire phone book?
Top and bottom touch.
When they touch, what does it mean? Okay, now let's think about it. One bookmark is marking the first page of the phone book that may contain the name that you're searching for. The other bookmark marks the last page that may contain the name that you're searching for. If both bookmarks or post-its are on the same page, it means that one page is the entire range that may still contain the name that you're searching for. So when they are on the same page, you cannot quit just yet, because the name that you're searching for can be on that one page right now. Okay? But after that one comparison, and that one page does not contain the name that you're searching for, then you can say it's not there. Okay? All right. Well, that's really helpful. Okay? Because how do I use concepts in programming to keep track of those two post-its or bookmarks? We don't have any bookmarks in programming. I mean, I know you have bookmarks in the browser, but that's not the same kind of bookmark. What if I don't have bookmarks, instead I have page numbers? Would that work? So on the little whiteboard, I keep track of the page number of the first page that can contain the name that I'm searching for, and on another little whiteboard, I keep track of the page number of the last page that may contain the name that I'm looking for. Would that work? It works the same way. I mean, it's just that it's not as tactile, because now you have to write on a piece of paper the page numbers and erase it and keep track of all those numbers. But it still works, right? Because it's just a number. A page number is nothing more than just a number. Is that working? Okay. How do we translate that into our algorithm here? Yep.
You make two variables, and then you assign the top variable to whatever you just changed it to, +1.
Mm-hmm.
And then the second one is the bottom one, and you do that one -1.
Okay, so we'll let variable b be the index of the first element in the entire array that may contain the value k, and then we'll use e be the index of the last element in the array. Okay. Yep. Thank you. Keep forgetting. I wonder why.
There's usually somebody in the bathroom.
Usually, but
When
not
it's
on
not
the
you.
not on the last Thursday. I actually forgot completely on last Thursday. Okay, so we'll have two variables. Okay, b is the index of the first element in the entire array that may contain k, which is analogous to the page number of this thing here, and then e is the page number of this thing here. Okay? So now that we have b and e, let's see what we can do with the loop here. Okay. All right. The first thing is, with b and e, I kind of have a way to determine this portion now, right? The index of the element that I'm supposed to compare to, it is just b plus e divided by 2. It's the middle one, okay? But since I might need to do that several times, I'm going to use a variable to store that. I'm going to say m is just b plus e, the whole thing divided by 2. And yes, sometimes if they don't work out well, there's a 0.5 here and so on. I'll deal with those later, because remember what I said a little bit earlier. If you're one page before or one page after, as long as you're close to the center, you'll still be okay. So I'm not too worried about this part here. I can deal with it later. All right. So now my TBD becomes m, right? Because now I can keep track of where's the beginning, where's the end, and what I want to compare to is really right in the middle of the entire range. Cool. So I'll call this revision 5, and then we'll go to revision 6. So here's revision 6, and in revision 6, let me double check something. I'm kind of worried. Oh, okay, I did. I thought I did not turn on the recorder. But the first class went through the same topic today, so it would still be okay, even though it's not totally okay. Okay, so now when you look at revision 5, it's good. It's really helpful, because now we know a way to define which range of the entire array may still contain the value that we are searching for. We know how to express which item we want to compare to the key. And there's only one thing left, which is if I just have a loop like this and a comparison like this, nothing is going to change. I can do this, for eternity, and nothing is going to change. So I have to do something to get us out of the loop. Okay. So M has to be updated eventually. But M depends on B and E, which means I probably want to do something about B and E. When we look at the example here, okay, I'm going to use a highlight feature here to kind of highlight which portion of the array may still contain the value that we are searching for. So after the first comparison, okay, before the first comparison, the entire array may contain the value that we are searching for. I'm just going to highlight it with a color. After the first comparison, which is against the value of 52, we rule out everything, including item 16 and everything before that. So that means what is remaining is this portion here that can still contain the value that we are searching for. After the second comparison, we rule out everything on and after item 24. So what is remaining is only this portion. After the third comparison, we only have 3 items left. And then after the fourth comparison, we have 1 item left. After the fifth comparison, we got nothing left, and that's how we know, okay, we are done here. Okay, so what we want to do is to say, with this case, okay, how did we transition from column A to column B? What got changed? The beginning or the end? The beginning.
B
got changed. Okay, so and it got changed because of what result of the comparison? 52 is less than 56. Okay, so I will go as far as I can today. Okay, so what we need to do. Okay, I'm just going to denote this part here. Since everything is being recorded, I can pick up from exactly this point next time. So what we want to do is I know we have to do something like this. We are comparing A bracket M with the value of K. Okay, we know that we're going to do that. With any comparison of numbers, we have 3 possible outcomes, right? So the 3 possible outcomes would be, one is equal to, the other one is less than, and then the last one is greater than. So the question is, what do we do with each case? With equal to, it's great. Eureka. Okay. With less than, we have to change something. What do we change when it's less than? Okay, when A bracket M is less than K, then means A bracket M minus 1 also is going to be less than K, and so on. So we are moving B in this case. Okay, so B gets something. We'll talk about this next time. You're correct, but I don't want to just rush through the discussion. So the other one is going to update E to something. Okay, to something. Right. Now the important part is we know that we have to change them, because as long as for each iteration I'm either changing B or E, or they're equal to, which means I can get out, I know I'm making some progress with each step. Okay, and we're working to the goal of getting out of the loop one way or another. Okay, so next time when we meet on Thursday, we'll take a look at the question marks and say, but how do we update B and E? And just in time for the version to come back to work. Perfect, exactly. 5 minutes.
You gave it out at the perfect moment.
9 o'clock?
Yep.
9 o'clock.
9 o'clock one is here. Oh, I already crossed out the names that are not there, but you might want to, you can just overwrite it.
Yeah. Thanks.
Professor Ted. I apologize for dozing off in class.
Okay.